So now that we have the basics of the dot product under our belt, let's talk about some geometry. First, recall that in Rm, the distance d between the origin and a point with coordinates x1, x2 down to xm is given by the formula d equals the square root of x1 squared plus x2 squared plus dot 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 plus xm squared. If we identify v with this point, then this tells us the length, or what's more commonly called the norm, of the vector v, which we denote by placing v in absolute value bars, is the same as this distance d, the square root of x1 squared plus x2 squared plus dot 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 plus xm squared. And we can recognize the sum under the square root as the dot product of v with itself. More commonly, you'll see this expressed as the relationship v dotted with itself is the norm of v squared. So this gives us some insight into the geometric content of the dot product. So if we have a pair of two-dimensional vectors, u and v, and we can look at their difference, u minus v. This forms our nice triangle. Since we're in the plane, we can think about the angle between these two vectors, which we'll call theta. As usual, our angle is always measured counterclockwise. So if we dig back to a course on trigonometry, you'll remember that the law of cosines tells us that if we take the square of the green side length, that's the norm of u minus v squared, that's equal to the square of the blue length, that's the norm of u squared, plus the square of the red length, that's the norm of v squared, minus twice the length of the blue side, which is the norm of u, multiplied by the length of the red side, that's the norm of v, times cosine of our angle, theta. Using what we know about the square of the norm and the dot product, we can rewrite the left-hand side of this equation as u minus v dotted with u minus v. We can simply FOIL to get u dotted with u minus u dotted with v minus v dotted with u plus v dotted with v. Since u dotted with v and v dotted with u are the same, we can rewrite this as the norm of u squared minus 2 u dot v plus the norm of v squared. Replacing the norm of u minus v squared in the law of cosines gives us replacing the norm of u minus v squared in the law of cosines gives us the equation the norm of u squared minus twice u dotted with v plus the norm of v squared is equal to the norm of u squared plus the norm of v squared minus twice the norm of u times the norm of v times cosine of theta. We can, of course, cancel the terms that appear on both sides, and we'll be left with u dotted with v is equal to the norm of u times the norm of v multiplied by cosine of theta. This provides us with a mechanism to measure the angle between two vectors. So we can see that cosine of theta is equal to u dot v divided by the norm of u multiplied by the norm of v. You can also think about this as u divided by the absolute value of u, which of course you could also think about as the dot product of the two unit vectors u scaled by 1 over the norm of u, dotted with v scaled by 1 over the norm of v. To find the angle between the two vectors u and v, we simply need to use the inverse cosine function to get at theta. Now I should mention that this works for vectors of any dimension. However, we're primarily going to concern ourselves with vectors of 2 dimensions because they're easier to visualize. So, as an example, let's compute the angle between the vectors u, which has coordinates 1 and 1, and v with coordinates root 3 and 3. We'll measure the angle between the vector u and the x-axis, the vector v in the x-axis, and then we'll be able to take the difference between them. So first off, we're going to compute the norm of v and the norm of u. So the norm of v is the square root of 3 squared plus 3 squared, which gives us 12, or twice the square root of 3. And the norm of u is the square root of 2. We're going to use the unit vector e1, which points in the x direction. And we'll start off by computing the dot product of v with e1 is equal to the norm of v times the norm of e1 times cosine of theta. We can replace the norm of v with twice root 3 and the norm of e1 with 1. If we divide both sides by 2 root 3, we see that cosine of theta is equal to 1/2. So this tells us that the angle between the x-axis and the vector v is pi over 3. We can play the same game with the vector u. We'll compute u dotted with e1, which is equal to the norm of u, the norm of e1, cosine of phi. The norm of e1 is 1, and the norm of u is root 2. Dividing both sides by root 2, and then rationalizing, we see that cosine of the angle phi is root 2 over 2. And this tells us that phi must be pi over 4. So now we can see the angle between the vector u and the vector v measured counterclockwise is pi over 3 minus pi over 4. And that, of course, gives us pi over 12. So if we had simply used the formula, theta is equal to arc cosine of u dot v divided by the norm of u times the norm of v, then we would have come out with arc cosine of root 3 plus 3 divided by the square root of 2 multiplied by 2 root 3, which is the same thing as twice root 6. If you had asked a calculator to compute this value for you, you would get something along the lines of 0.261799387799. This, of course, is a decimal approximation to pi over 12 that I retrieved from Desmos, but it is not at all obvious that this is pi over 12. So of particular importance here is to note that we can use the dot product to detect when two vectors are perpendicular to one another. Namely, if two vectors are perpendicular to one another, the angle between them is pi over 2. Because cosine of pi over 2 is 0, we get simply 0. So of course, we define two vectors, u and v, to be orthogonal if their dot product is equal to 0. And that's it for the basics of the dot product.